Okay, welcome back. Let's take a look at the next little set. I think we're looking at problems 11 through 15. So here we go. Now I find these to be, the first two are pretty easy, pretty direct. We'll just see how it goes. So again, in a proof, what we always want to do is select the side that we want to mess with, and then leave that other side alone until they're reflexive. So this particular problem, I think what I would probably do is, of course, start with the left side. And the first thing that I noticed, and again, this is not the only way. So if you did it differently, it's okay. There's nothing wrong with it. But I noticed that cosine squared is 1 minus sine squared. Now, beneficially, what that does is it means I'm looking for things over here that are sines. And now on my left side, everything that I do have is in the term of sines. Then what I should also notice is that every time in algebra you had something that is a difference of squares, like a squared minus b squared, that is a plus and a minus b, that whole conjugate field. And if you look right here, that's what I do have. 1 is a perfect square, and sine squared is a perfect square. So I have 1 plus sine times 1 minus sine. Now, again, some of you would have probably attacked and made a common denominator, and I'm not saying that that is an incorrect way to do this problem. I just saw a method that appeared to be a little bit more efficient. And so I noticed those two things canceled. And then, of course, by the distributive property, we're sitting right here. And then, of course, 1 minus 1 is 0. So we end up with sine equals sine, and that kind of does it. Now, there might be another way that's a tiny bit faster, but that was a pretty efficient method. Now, over here, I suppose the way I would probably personally attack that is by first just looking at the fact that this term is in sines and cosines, and this one is in reciprocals of sines and cosines. So if we were to multiply the numerator by cosine sine and the denominator by cosine sine, let's see what happens. Let's see, this is secant and cosecant theta. Now, we have a list of identities that are very, very useful. So I'm going to go ahead and hit pause for 1 second, okay? Let me go ahead and stop this, and let's go ahead and... Okay, so let's go back to that. Sorry, I got a phone call in the middle there. But here's what happens. When you multiply these two together, a cosine and a secant are in fact reciprocals of each other. So this cosine and this secant we're going to cancel, and all I'm left with is sine. Now, by the distributive property, the sine and the cosecant also cancel because they are also reciprocals. So I get cosine. Now, if you peek over here, that's looking pretty good because that's what I want. Now, the part that people kind of mess up is that the distributive property holds in this top one, but in this bottom, all of these are one big block of multiplication, and the cosine and the secant cancel, and the sine and the cosecant cancel. And so I end up with sine minus cosine divided by 1, which is exactly what I wanted to have. And we're done. That was a nice, easy one. And then, of course, our last little piece, this is going to be kind of a funny one. It's just a matter of just thinking about factoring. And that sometimes you get these things that look, they're very trig related, but you want to be able to do something to make them factorable. And so what I noticed is you could do this, let u be the cosine of theta. And so we would have 5u squared minus 13u minus 6. I don't know why I wrote 2 u's, but it's all right. And so we think through what it would be, and I'd have 5u times u would, of course, be 5u squared. And to get 6, it's either a 1 and a 6 or a 3 and a 2. And pretty quickly, since I'm looking for a number that's pretty big, I can see that a 3 and a 2 would work because 15 and 2 would make 13 if I had it in this area right here. But remember, u was the cosine, so we'd have 5 cosines plus 2. and we'd have a cosine minus 3. Now, you didn't really have to do that. Some people can just look at it and see that, and that's what I'm going to do on this problem. I notice the only way to get 2 sine squares is 2 sine times a sine. And because the number 7 is a prime number, one of these two numbers has to be a 7. It either has to be a 7 here or a 7 here. But notice that if I put the 7 in that order, I'd get a 14 and a 1, and there's no way to get a 5 out of that. So instead, what I'm going to do is I'm going to go ahead and make this one into a 1 and make this one into a 7 and see what happens. Now, I think a 2 and a 7 could make 5 if the 7 was positive and the 1 was negative, and I didn't have to take that intermediary step. And then, of course, the last one right here is just noticing what things have in common. And I notice these both have a 2, they both have a secant, and they both have a tangent. And if I took all of that stuff out, I have a 1 left. I took out the 2, I took out the secant, I took out one of the tangents, but there'd be 2 of them left. And that leads me to my final answer, because as we did in one of the earlier pieces, this is a difference of squares. 1 minus the tangent squared is 1 minus the tangent times 1 plus the tangent. And we're done. Hey, there we go. Hopefully that was helpful. Okay, see you back in class. Bye-bye.